13.8 billion years ago, our universe began as a single point in space of tiny hot particles mixed with light and energy and expanded, and is still expanding to this day, and as it expanded and took up more and more space, it cooled down. The tiny particles began to cluster and formed atoms, which clustered together, and over time, those clusters upon clusters became stars and galaxies 250 million years after the Big Bang. So, specifically, how are stars formed? A star forms when interstellar medium, the matter between stars consisting of gas and dust the sizes of atoms and clumps of molecules, begins to collapse under its own weight. This can only happen if the gravity of the interstellar medium cloud is stronger than the heat, magnetism, and rotation competing with it. Due to Newton's laws of universal gravitation, all objects exert a gravitational force. All interstellar medium clouds have a gravitational pull, but they only will collapse if their gravity is strong enough against these factors. Even though all atoms have a gravitational pull, individual gas and dust particles do not exert a gravitational force strong enough to incidentally clump together due to the force of heat counteracting gravity. In fact, 10 to the 57 atoms are required to begin forming a star. For reference, all the sand of Earth's beaches is 10 to the 25th. Much less than that amount. The collapsing interstellar medium cloud eventually breaks into dense fragments that heat up as they continue to collapse. The cloud eventually stops fragmenting when it becomes so dense that radiated energy has more difficulty escaping, causing temperatures and pressure to rise. The body is considered to be a protostar once fragmentation ceases, although it is more of a dense region that has a photosphere at this point. There's something called a brown dwarf, where a protostar fails to even burn its fuel. Their evolutionary track ends at this point. Successful protostars are hundreds of times bigger than the sun and have a luminosity thousands of times greater than it, but it is about half the sun's temperature. It is now plottable on the HR diagram. However, by stage 5, it is now only 10 times the sun's size while its temperature continues to rise. Eventually, at stage 6, it is now a true star. The temperatures of its core eventually rise to around 15 million degrees Kelvin, the temperature where nuclear fusion can occur. This is the point where the star ceases collapsing and is now considered a main sequence star. The reason the collapsing stops is because the heat of the star's core creates large amounts of pressure that counteract the effects of gravity. This is called hydrostatic equilibrium. From initial interstellar cloud collapsing to star formation, this process takes around 1 million years. Although a star spends 90% of its life in the main sequence, 10 billion years, it eventually begins to run out of hydrogen fuel for nuclear fusion and continues to go through more stages before it reaches its death. Over a star's lifespan, helium becomes more abundant in its core than hydrogen as it burns its fuel. 10 million years after a star has been in the main sequence, hydrogen depletes from the very center of its core and hydrogen burning moves to the upper layers of the core. Hydrostatic equilibrium is challenged because the now majorly helium core relaxes its exertion of pressure more than it used to. This causes contraction within the inner core of the star, accelerating as the star depletes more and more of its hydrogen reserves. The star cannot burn the helium because it is not hot enough for the nuclear fusion of helium to occur. Meanwhile, the layer containing hydrogen surrounding the core is keeping the star alive. This is called hydrogen shell burning. As the mostly helium core contracts, rising gravitational energy causes the star to become even hotter, and hydrogen burning accelerates even more. The star is 3 times the size of the sun at this point and is considered to be a subgiant. The helium core continues to contract as it fuses more hydrogen to helium at an accelerating rate. Pressure and heat created in the core results in the expanding of the layers outside the core. These layers become cooler as they expand, and the star eventually becomes a red giant 100 million years after it was a main sequence star. At this point, the star may be 100 to 1,000 times bigger than the sun. A few 100 million years after the star was considered to be in the main sequence, it begins to burn helium in its core instead of hydrogen. This is because the temperature has risen to 10 to the 8th Kelvin, which is the point at which helium is able to become carbon through nuclear fusion in a process known as the triple alpha process. At this point, the star undergoes even more changes. The high intensity of heat now present in the star's core causes electrons to be stripped from the nuclei they were once electromagnetically attached to. A quantum mechanics rule known as the exclusion principle causes these electrons to be prohibited from touching each other or being squeezed too close together. If compression in the star squeezes these electrons too close together, they will resist being further compressed even if they are squeezed to the point of contact. This creates what is known as electron degeneracy pressure. At this point, the pressure created is nearly entirely what is resisting the force of gravity for the star, not thermal pressure like it used to be. This causes instability because now, as the helium burns, rising thermal temperature does not create meaningful amounts of pressure. Normally, with the support of thermal pressure, the star would have expanded and cooled, and the core would have stabilized, but now the pressure does not rise as nuclear reaction rates increase, and the temperature rapidly increases. This is known as the helium flash. The core heats up so rapidly that eventually thermal pressure becomes more present than electron degeneracy pressure, the state the star used to be in. The core restabilizes and returns to normal. Now, temperatures in the core have risen even higher, and now helium is beginning to be fused into carbon. However, luminosity does not increase during the helium flash, and the star expanded and cooled during this process, resulting in a reduction in energy output. But the surface temperature is now higher than it used to be in the red giant branch of the HR diagram. This entire process occurs in 100,000 years. The helium fuel lasts the star a few tens of millions of years after the helium flash. Like before in stage 8, where hydrogen would burn in the core from inside to out, leaving helium behind as the core contracts until all that is left to burn is the hydrogen shell, this time helium burns, leaving a carbon core. Like before as well, temperature increases as the core contracts, causing increasing reaction rates. However, now the carbon core is surrounded by both a helium-burning shell and on top of that, a hydrogen-burning shell. The layers outside of these, the envelope, continues to expand. Temperatures in these shells increase in luminosity and temperature. Directly related to hydrostatic equilibrium, or the cessation of it, stars will eventually die. At some point, a star will burn out all of its fuel, and there will no longer be enough thermal pressure to counteract a star's gravitational force. In stars bigger than the Sun, temperatures would be able to rise high enough for nuclear fusion to make even heavier elements and keep equilibrium between pressure and gravity stable. But in stars like the Sun, temperatures do not reach high enough to keep equilibrium for as long. Eventually, electrons become degenerate again and the core stops compressing. Temperatures stop rising, and nuclear fusion only happens between carbon and helium at the inner edge of the helium shell, creating some oxygen. The amounts are not significant enough to create any heavier elements, and the nuclear fusion that once powered the star and its core completely ceases. The remaining parts of the star that burn are its shells, as the rest of the star expands and cools to 300 times the size of the Sun. The helium-burning shell has helium shell flashes, caused by the intense levels of pressure now present, causing fluctuating levels of radiation in the outer layers of the star, and causing those layers to pulsate, heat, expand, cool, and contract. The pulsations grow in size as the temperatures in the core increase and nuclear shell burning intensifies. At this stage, burning is very unstable. Most of the star's outer layers become ejected into space in less than a few million years because of the intense radiation and instability in the star. At this moment, the star consists of a hot, dense, and luminous carbon core with the helium shell forming carbon and oxygen, and outside of this, the ejected outer layers spread out throughout space as a giant dust and gas cloud, roughly the size of our solar system. The cloud eventually diffuses after a few tens of thousands of years to the point where it is no longer visible. The star fades and cools eventually. The carbon core is now visible because the outer layers diffused into space over several tens of thousands of years. It has compacted down to the size of Earth and only shines because of stored heat and is dim due to its small size. This is a white dwarf. White dwarfs can have explosions on their surfaces when matter falls onto them. These are called novae, singular nova. After it lasts for a few days, they return to their normal state within a few weeks or so. However, this only occurs in binary systems, where two stars are gravitationally bound together and orbit each other. If the two stars are close enough together, and one of them is a white dwarf, it can pull matter from the other star, and the binary system is then called a mass-transferring binary. Only then can novae be created. This extends the stellar activity lifetime in the white dwarf and can be repeated hundreds of times. As isolated white dwarfs dim over time, however, they become black dwarfs. It is no longer being compressed by gravity due to it still having electron degeneracy, as well as it being very dense. It remains as a cold and dense dead star. Stars bigger than the Sun, or high-mass stars, evolve faster and have different stages than stars like the Sun. This is caused by their larger mass and stronger gravity generating much more heat, but up until stage 9, their evolutionary track is the same. High-mass stars have a much more stable stage 10. There are no helium flashes, and there is not as much of a pressure contribution from electron degeneracy. And like mentioned before in stage 12, larger stars are able to burn heavier elements past helium, such as carbon, oxygen, and even heavier elements like neon, magnesium, and silicon, all the way up to iron, that resides at its core. Eventually, they become a red supergiant. As each element burns through, nuclear reactions speed up and central temperatures climb even higher. Reactions speed up so fast, actually, that iron burns through in less than a day by the time it reaches that element. Equilibrium ceases when the star becomes iron-cored. Gravity overwhelms any thermal pressure left pushing outwards from inside the star. Eventually, the core becomes so dense and compacted that the electrons do end up touching each other. The core stops compressing briefly and rebounds, causing an enormous explosion known as a core collapse supernova. A supernova is over 1 million times brighter than a nova, and billions of times brighter than the sun. There are 2 types of supernovae, type 2 being the core collapse supernova just described, and type 1 in comparison does not have very much hydrogen compared to type 2, and occurs in binary systems only. Type 1 occurs when a white dwarf obtains so much mass from its partner that it can no longer support its own weight and collapses onto itself. This is also called a carbon detonation supernova because the white dwarf begins fusing carbon right before it dies. This marks the end of a high-mass star's life, destroying the star itself. However, there is another possible outcome that may occur as a high-mass star reaches the end of its life. In stars that have a Type 1 explosion, nothing remains of the parent star. However, in Type 2 supernova explosions, there is a potential for a stellar remnant, an extremely compact piece of the star's inner core. This is called a neutron star. They are nearly 1 billion times denser than a white dwarf and are supported by neutron degeneracy pressure, so they do not compress further. But if the neutron star is greater than 3 solar masses, it will infinitely collapse on itself and become a black hole. Gravity is so intense that not even light itself can escape. This is the final stage a star can reach. Only very high-mass stars, main sequence stars 25 times the sun's size, can become black holes at the end of their lives. Due to the law of angular momentum, black holes spin rapidly. Imagine you're sitting in a swivel chair, holding heavy weights. If you hold them away from your body and spin in the chair, you spin slowly, but when you bring them closer, you spin quickly. This applies to the black hole and its extremely high density. That concludes all the stages of stellar evolution.